One of the most common mistakes in machinery risk assessment is analyzing hazards in isolation instead of analyzing hazardous situations. A table may list moving mechanical parts, electrical energy, pneumatics, sharp edges, or high temperatures, but the document still fails to show who may be exposed, during which task, and in what state of the machine. From the perspective of ISO 12100, that assessment is incomplete. A more sophisticated matrix or a more precise numerical calculation will not fix the problem. If the scenario itself has been defined incorrectly, the result will have limited value as well. This is the Safety Software Podcast. In this episode, we will walk through a practical approach to risk assessment in accordance with ISO 12100, using a packaging machine as an example. Not as an exercise in filling out a table, but as an engineering decision-making process. ISO 12100 provides the structure for that process. First, we determine the limits of the machinery. Then, we identify hazards and hazardous situations. Next, we estimate the risk and evaluate whether further risk reduction is required. If it is, we introduce risk reduction measures and assess the situation again. The process is iterative. The assessment does not end when a safeguard is entered into the relevant column. We still have to verify whether that safeguard actually reduced the risk and whether it introduced a new problem in the process. The standard does not prescribe one mandatory scoring method. It does not require HRN, risk score, or any specific risk matrix. A numerical method is a supporting tool. It can bring structure to the assessment and improve consistency between projects, but it does not replace engineering analysis. This matters because, in many organizations, the method gradually starts to become the focus of the exercise. Teams spend a great deal of time debating whether probability should be scored as 2 or 3, while spending far less time checking whether the correct scenario has been described in the first place. If an operator opens the machine several times per shift to clear a misaligned product, that is not a minor operational detail. It may fundamentally change the assessment of exposure. And if the designer does not know that, because the assessment was carried out only from drawings and design documentation, the result may look highly precise while describing a machine that does not really exist in practice. That is why the assessment begins with the limits of the machinery. We need to define its intended use, expected users, modes of use, range of movement, materials, energy sources, working environment, the space around the machine, its foreseeable service life, and the relevant phases of its life cycle. Automatic production is only one of those phases. We also have transport, installation, commissioning, adjustment, changeover, material replenishment, cleaning, troubleshooting, clearing faults and blockages, maintenance, repair, and eventually decommissioning and dismantling. In practice, many of the most serious human exposures to hazards occur during precisely these non-production phases. It is also important to understand the concept of reasonably foreseeable misuse correctly. This does not mean inventing extreme or absurd operator behavior. It means considering behavior that can reasonably be anticipated from the way the work is actually performed. If clearing a jammed carton takes 30 seconds when the official procedure is followed, but 5 seconds if someone simply reaches through an opening, the designer should at least recognize that the shortcut will be tempting. If every opening of a guard requires the operator to work through several HMI screens before restart, people may start looking for a faster way. If an adjustment requires a clear view of the mechanism, but a complete stop makes it impossible to observe the effect of that adjustment. Sooner or later, someone may try to perform the task while movement is still enabled. Designing a safe machine does not mean assuming ideal human behavior. The assessment has to take account of real working ergonomics, time pressure, the frequency of interventions, and the way people actually respond to process disturbances. The example of a carton forming and closing station shows clearly why treating a machine as one single object is not enough. The automatic cycle is straightforward. A flat carton is picked, formed, transported, the flaps are folded, and the package is closed. If we looked only at automatic operation, the number of hazardous situations would probably be quite small. The situation changes when the material is misaligned. A carton becomes jammed, the format has to be changed, or a sensor begins to report a fault. The same machine suddenly requires direct human interaction with the mechanism. In the example assessment, a number of separate situations were identified. That is the correct direction, because a single source of hazard can create very different levels of risk depending on the task. The carton-forming mechanism may be completely inaccessible to the operator during automatic production. The same mechanism becomes a direct source of hazard when a setter opens a guard to make an adjustment. The situation is different again for a maintenance technician who needs to observe the drive during diagnostics. In each case, the exposure, the state of the machine, the degree of access, and the possibility of avoiding harm are different. An entry such as mechanical hazard, moving parts, does not allow us to assess any of that. A useful description needs to identify the task and the conditions. For example, while clearing a deformed carton, the operator opens the side guard and gains access to the operating area of a pneumatic cylinder and the transport mechanism. Now we have something that can be analyzed. We can ask whether hazardous motion stops before access is possible, whether energy can be reapplied, whether automatic restart is possible after the guard is closed, and whether the operator could remain inside the hazardous area. The same applies to electrical hazards. Simply stating that the machine is supplied at 400 volts adds very little to the assessment. A much more relevant scenario is one in which an electrician opens the control cabinet during diagnostics, while some circuits must remain energized. At that point, we can assess the competence of the person, the method of access, protection against contact, labeling, the possibility of accidental contact with live parts, and the procedure for carrying out the work. Once the hazardous situation is properly defined, we can move on to risk estimation. In the example, HRN was used. It is one of the methods commonly used in industry, and it can provide useful structure, provided the team understands what it is actually assessing. The score itself is not the decision. ISO 12100 distinguishes between risk estimation and risk evaluation. First, we estimate the magnitude of the risk. Then we decide whether further risk reduction is required. That distinction matters because no value in a table relieves the designer of the responsibility to assess whether the solution reflects the state of the art and whether the hierarchy of risk reduction measures has been applied correctly. One of the more dangerous habits in practice is adjusting the scoring parameters to obtain the result the team expects. A guard is installed, so exposure frequency or probability is automatically reduced because, after all, there is now a safeguard. But every reduction in a parameter should have a technical justification. What exactly changed? Has access been physically prevented? Does opening the guard stop the hazardous movement? Has the energy or force been reduced? Does the operator no longer need to perform the task? If we cannot identify the actual mechanism by which risk has been reduced, changing a number in the matrix is only changing a number. The next issue is the hierarchy of risk reduction. ISO 12100 is very clear on this point. The first step is inherently safe design measures. Only then do we move to safeguarding and complementary protective measures. Information for use comes third. These three levels are not equivalent. If during the clearing of a jam, an operator can place a hand between moving parts, the first question should not be which interlocking device to fit to the door. The first question should be why the jam occurs at all and whether human intervention is necessary. Perhaps the material guidance can be redesigned. Perhaps the geometry can be changed. Perhaps a defective product can be removed from outside the hazardous area. Perhaps the force or energy of the mechanism can be reduced. Only when inherently safe design does not reduce the risk sufficiently should we move to guards, interlocks, light curtains, laser scanners, and safety functions. Going straight to instructions is a very weak solution. Many risk assessments contain measures such as train the operator, exercise particular caution, or use personal protective equipment. Sometimes such measures are justified, but they cannot replace a protective measure that could reasonably have been implemented through design. An instruction does not stop a drive. A warning sign on a guard does not prevent access. If the risk can technically be eliminated or significantly reduced, that option must be considered first. Once a safety function implemented by the control system becomes necessary, we need to describe very precisely what that function is expected to do. A note such as interlocked guard, PLD, is not enough. The function has to be defined first. For example, opening a particular guard must stop specified hazardous movements, prevent those movements from starting while the guard is open, and prevent automatic restart when the guard is closed again. Only after that do we determine the required performance level, or PLR, and design the function in accordance with the relevant standard. For example, ISO 13849-1. The order may seem like a small detail, but it has major practical consequences. The required PL should not appear in a project simply because the organization has adopted a rule that we always use PLD. It should result from the specific safety function and from the risk that the function is intended to reduce. We sometimes see machines in which the components have very good safety parameters and the calculated PL appears correct, but the overall design still has a serious flaw. A common example is a manual reset device, positioned so that the person initiating the reset cannot see the entire hazardous area. The input architecture, logic, and output elements can all be calculated correctly, but that calculation does not solve a poor control layout. The same is true of a light curtain. It may be wired correctly and achieve the required performance level, yet still be installed too close to the hazardous area. A person can break the beam and still reach the hazard before the dangerous movement has stopped. In that case, the problem is not the reliability of the safety function. The problem is the design of the protective measure as a whole. That is why validation cannot be reduced to checking whether the safety PLC reports any faults. We have to verify the behavior of the machine. What happens when the guard is opened during the cycle? Which movements stop and which remain active? What happens after the guard is closed again? Can the reset command itself initiate movement? What happens after power is lost and then restored? What happens if a sensor fails or a short circuit occurs? Can pneumatic energy still cause movement even if the electrical drive has been isolated? Can an element fall under gravity after the machine has stopped? Only this kind of verification provides credible evidence that the risk reduction measure works as intended in the assessment. We also need to remember that adding a protective measure changes the machine. Any change can introduce new hazards. A heavy, movable guard can create a crushing or trapping point. Relocating a control can reduce visibility. An additional barrier can force a service technician into a poorer working posture during maintenance. An unnecessarily complicated restart sequence after every short intervention can increase the incentive to bypass a safeguard. None of this is an argument against protective measures. It is an argument for reassessing the machine after they are introduced. A common mistake is to treat the safeguard as the end of the analysis. The team identifies a risk, selects an interlock, and closes the action. ISO 12100 requires us to verify whether the measure reduced the original risk and whether it created new hazards or increased other risks. Only then should the risk be estimated again. The same applies to residual risk. The term is often misused. A risk does not become residual simply because the team no longer wants to reduce it, or because the final result has moved into a green area of the matrix. The hierarchy of risk reduction measures must first be applied correctly. Solutions appropriate to the state of the art must be implemented, and their effectiveness must be verified. Only the risk that remains after that work can properly be considered residual risk. Information about residual risk should then be included in the instructions and other information for use where required. It is not a mechanism for transferring responsibility for an inadequate design to the user. The packaging machine example highlights another point that matters in practice. The most important risks are often not associated with the activities that occupy most of the machine's operating time. A machine may run automatically for 98% of a shift, while the significant risk exists during the remaining 2% spent clearing jams, making adjustments, and diagnosing faults. Designers usually know the automatic cycle very well. They know the cycle time, signal sequence, movement sequence, and drive positions. Much less attention is sometimes paid to what people do when the process does not run as intended. Yet, disturbances are exactly when people move closer to energy sources. They open guards, reach inside, use manual mode, ask a second person to jog a movement from the control panel, or try to observe a mechanism while making an adjustment. That is why an assessment carried out by a designer alone at a desk will often be incomplete. The team needs input from automation engineers, electrical engineers, mechanical designers, and safety specialists, but also from maintenance personnel and operators. An operator may point out a task carried out a dozen times a day that the designer never considered as a separate activity. Maintenance may know that one particular sensor regularly requires adjustment. An automation engineer may explain that, in a particular mode, not all drives are stopped. Only when those pieces of information are brought together do we get a realistic picture of how the machine is actually used. This is also where the role of a risk assessment tool becomes relevant. Software should not make engineering decisions for the team. It should not automatically declare a machine safe. What it can do is enforce consistency in the process. It can make sure that a scenario is linked to a person, a task, a hazard, an initial assessment, a risk reduction measure, a post-reduction assessment, and a verification result. It can retain the history of changes and show that a risk value changed because of a specific engineering action rather than simply being overwritten. This becomes particularly important in larger projects. Excel is not inherently a bad tool. A very good risk assessment can be carried out in a spreadsheet. The difficulty begins when a spreadsheet is expected to act as a database, a version control system, a collaborative engineering platform, and a documentation generator at the same time. At that point, it becomes easy to change a parameter without leaving a trace, copy a row from a previous project, remove a protective measure without updating the later stages of the assessment, or generate a report that shows only the latest state of the file. 2 years later, nobody remembers why a particular parameter was reduced or why a specific safety function was assigned PLRD. The decision trail is extremely important in machinery safety, not only for an audit. The machine will later be modified, personnel will change, a new version of the design will appear. There may be a failure or an incident. In all of those situations, the ability to reconstruct the original engineering reasoning has real value. We should be able to see which scenario was assessed, which assumptions were made, why a particular measure was selected, how its effectiveness was confirmed, and why the remaining risk was considered adequately reduced. This is one of the reasons safety software treats risk assessment as a process of data and engineering decisions rather than simply as a way of generating a final PDF. The report is necessary, but it should be the output of the work. It should not be the objective of the work. One of the best ways to test the quality of a risk assessment is to select one real hazardous situation and follow the entire decision path. Take the clearing of a jam on the packaging machine. Do we know why the jam can occur? How often does someone have to intervene? From where does the person gain access? Which elements can move at that point? Which forms of energy are still present? What was the initial risk estimate? Before the interlocked guard was selected, did the team consider eliminating the cause of the jam or changing the method of access? If a safety function was introduced, what exactly is its specification? How was the required PL determined? Was the function validated? What happens if the sensor fails? Did the protective measure introduce a new hazard? Why was the remaining risk considered sufficiently reduced? If the documentation can answer those questions, we have a risk assessment that can be defended on engineering grounds. If the answer is reduced to a row reading moving parts HRN40, guard installed HRN2, risk acceptable, then what we primarily have is a table. That is the difference. A risk assessment, in accordance with ISO 12100, should influence the design while the design can still be changed. It should influence geometry, access, the positioning of components and controls, operating modes, automation, safety functions, service procedures, and the instructions. If the assessment begins only after the machine design is complete, when the mechanics are built, the software is written, the guards have been ordered, and shipment is planned for the following week, the options for proper risk reduction are already limited. At that stage, the team is no longer looking for the best solution. It is looking for something that can still be fitted into the finished machine. This is why risk assessment should be updated throughout the project rather than carried out once at the end. The quality of an assessment is not demonstrated by the number of pages in the report or by the complexity of the scoring method. It is demonstrated by the ability to trace every significant engineering decision from a specific hazardous situation through risk estimation and the selection of a risk reduction measure to verification of effectiveness and evaluation of the residual risk. If that path cannot be reconstructed, the problem is not only the documentation, the problem is the way the risk assessment itself was carried out. This was the Safety Software Podcast. More practical material on ISO 12100, machinery risk assessment, safety functions, and technical documentation is available at safetysoftware.eu.